Give the talk. Which one? You think about that perfectly. So you have to become new.
Good afternoon. I'm very happy to welcome Professor David Buckley, the senior astronomer at the South African Astronomical Observatory. He is a leading figure in optical astronomy and astronomical instrumentation. He has played a central role in the development, commissioning, as well as scientific exploitation of the South African Large Telescope. His science interest spawns from time-domain astronomy, impact objects, as well as multi-wavelength physics. He has made seminal discoveries and results in transient science. He has been actually PI for the SALT transient program for several years. He's also the South African PI for the transient detection and the follow-up study Rubin observatories. So Buckley has been very deeply involved in the building observing capabilities in the southern hemisphere, and also mentoring next generation of astronomers through collaborations with national facilities as well as classic facilities, including our own associate. Like here, he was in Bangalore for the 10-year celebration conference. He did the talk, and he's here. He's going to spend a couple of days here. So today he's going to share some highlights and insights from the cutting-edge transient studies and future prospects.
Thank you very much for those kind words, and it's a pleasure to be back here. I'm amazed that it's actually, when I think about it, it's over 6 years since I was here. I was here in November 2019, just prior to COVID. And at that time, I've been to a few different institutions around India, and who knew what was going to happen like the next year. And in fact, I attended the Kavli IAU transient meeting in Cape Town in February, and there were a few people that came on flights from Asia who weren't feeling very well. Anyway, I'm going to, as Gulab said, talk a bit about the SALT transient program, which I've been leading for about 9 years now, since it began. And it's one of the so-called large science programs on SALT, and it's been one of the most productive, and one that has involved people here in IUCAA as well, particularly in the area of compact binaries, X-ray binaries. So most of the talk I'll be giving some highlights. I can't cover everything, and I'm going to be somewhat biased into the areas of my own interest, but I've sort of got interested in other areas as well, so I'll try and touch on those. And I'll end up with a sort of overview of the future. I mean, we all know that Rubin is now coming on stream. The LSST should begin imminently, although I just saw an email today that they had a vacuum problem with the cameras. But it's going to be there soon. And so what we've been doing with SALT follow-up will extend to as a follow-up with SALT of transient is going to be a whole new ballgame with discoveries from LSST. And we have our own group that I lead in South Africa, but we're also collaborating with Transient and Variable Star collaboration with LSST. And South Africa's buy-in to LSST was through in-kind contributions, of which time on SALT is one of those contributions. So let me proceed. And I think for this audience, I don't need to say why transients are so important and why they've become such a compelling field of discovery in the last couple of decades. It's basically taking the exploitation of time domain from new discovery space and looking at phenomena now at timescales that are on accretion timescales, so millisecond timescales, but also longer, because some types of objects evolve over days, weeks, months, years even. And so transients cover a wide variety of classes, and they can be studied and discovered at many different wavelengths. And it covers everything from the most energetic events you can possibly conceive of, like this artist's impression of the first kilonova, which was an electromagnetic counterpart of course, gravitational wave event that probably many of you in the audience were co-authors of that massive paper. Nova eruptions, which we've known about nova for 100,000 years. It's basically a wide class now. And the SALT transient program has been addressing many of these and following up from the discoveries made by some of these other facilities that are shown here. So some facilities we have ourselves in South Africa. They're optical wide field telescopes that are finding optical transients. The most recent one being MERLIT, which is a telescope that follows MeerKAT for looking at the possibility of radio transients being detected in the optical if you have simultaneous observations. And of course, there's many types of dedicated facilities which are, built just to find a certain class of transients, like the Assassin network for supernovae, and the Atlas network for solar system objects. But those and many others are finding transients as a byproduct of their main science driver. So even Gaia, which wasn't designed to look for transients, has found, of course, many transients. And so we've been exploiting the discoveries by other facilities, and with our program on SALT, been following up optically, but also coordinating with colleagues who have access to other facilities. And of course, AstroSat is one of them in relation to the X-ray binaries. So this program sort of had its early days in 2016. So it's actually 10 years ago, and not so large allocation of time back then. It was a sort of pilot program, but it's expanded now to become one of the biggest programs that's run on SALT. I think what we've learned from this over the period of the last few years and how it's evolved, it's not a fixed program in the sense that we're always adding new classes and new types of objects. So the sort of dominance of one class of objects may change over the years. For example, when we started, MeerKAT wasn't operating, so we weren't doing radio transients. Now radio transients an important group. Likewise, eROSITA, when that came along, was operating. We were following up a lot of those, and I'll talk about some of that. So this is the program I'm talking about. It's grown to an allocation of something like 300 kiloseconds a semester, with a high fraction in what we call P0 time, which is the highest priority, if you like, target of opportunity override, which is what you need for many rapid follow-ups of certain types of classes of transients. The nice thing about it, although SALT can't be pointed anywhere in the sky at any one time, you've got this restricted viewing annulus on the sky. Nonetheless, for a lot of the science, it's quite okay to be able to sort of wait until the object gets into the field of view. And the nice thing about it is that we have a variety of instruments all available at the same time. So it's literally like 30 seconds to flip between one port and another to another instrument. And the data is available, the raw data is available immediately after the observation, and the pipeline process data is typically available by the morning after the observation. So, as I say, it's been successful. There's over 130 refereed papers that have exploited the SALT data to date, many involving other multi-wavelength facilities. It's also a widely encompassing program of collaboration. So at the moment, there's five South African institutions involved, all of the, or four of the SALT partners, of which IUCAA has been an important contributor. And in total, we have something now about 36 co-investigators, which include 12 graduate students. And this has been really successful for many graduate students, and particularly I'll mention one in respect to the Novi. And then, as I say, it's evolved over time. So we now have MOUs with other groups, for example, the eRosita group, and recently we've been collaborating with the Einstein Pro group at the NAOC as well. So I was saying that, you're a bit restricted with SALT. You can only observe a narrow part of the window, about 12% of the sky at any one time in that annulus that's shown here. Nonetheless, because it's a Q-scheduled telescope and because in many cases, the objects don't have to be observed right immediately, we're still able to do good transient science. There's a picture of the facility, which probably you've seen this many times. It's a nice, dry, dark site, perhaps not the best seeing site, but still a very good facility. And now that photo is completely outdated because there's something like 21 other telescopes there now, many of them involved in transient science as well. And the heart of it, of course, is this big array of 91 hexagonal mirror segments, making a 10-meter diameter telescope. And I was so delighted to hear at the AstroSat meeting the announcement that the 13.7-meter NLOT and the 3.7-meter telescopes are now going to be built in India, which I've had a sort of interest in over the years. So, of course, what we do, types of observations, I'm not going to go through all of these, but the obvious thing is can do photometry, and we have instrumentation that's capable of doing time resolved photometry down to about 100 milliseconds, a tenth of a second time resolution. So that's used for studying periodic phenomena, orbital or spin modulated objects, QPOs, quasi-periodic oscillations, aperiodic flickering, all that sort of stuff, and color information if you do it with filters. Spectroscopy, though, is the real heart of the telescope and where most of the observations are done because, a photometric point or a light curve only tells part of the story, and really you need a spectrum to classify. So a lot of what we do is classification spectroscopy, and then for certain objects, follow up intensively to, say, obtain rate of velocity curves or changes in spectral energy distributions, etc. And for some objects, particularly some that I'm interested in, we do spectropolarimetry, and I'll talk a little bit about that. So the instrumentation we have, I won't dwell on this too much, but we have the main workhorse instrument at the prime focus. This is a sort of all singing, all dancing spectrograph with many modes. The astronomers like to sort of talk about it as being the Swiss Army knife of instruments, which sounds great, but the engineers hate it because there's so many modes and so many things that they've got to fix because, with something that has so many moving parts, it's sometimes something which is challenging. But we have that instrument, and it's been a great resource. And we have the imaging instrument Salticam. We have a high-resolution fiber-fed spectrograph for brighter objects. So that's been used extensively for observing things like novae. And then more recently, although we haven't really exploited it yet, is the NIRWALS near-infrared integral field unit spectrograph. And I'm sure that some of the people within the SALT transient program will want to use that going forward to observe. Yeah. And future instruments, well, this is now unfortunately on hold. this was the last instrument that I had a formal responsibility for as the PI, but regrettably, because of demands of funding and priorities, this future extension of the spectrograph to a dedicated visible red beam that would allow, two-beam spectroscopy is currently on hold, but hopefully one day it might be realized. So in terms of the program, the SALT Transient program, as you heard, there's lots of people involved in it. And I'm the PI, but I think of myself as an orchestra conductor, right? So I'm just the person in the middle who then gives responsibility for like the string section or the woodwind section or the brass section or whatever to other people. They're the head of those sections. So I'm not really a Blazar AGM person. Marcus Butcher, who's an astronomer at Northwestern University, Saatchi Chair in Astronomy, he's a theoretician in Blazars, and other people, they lead the Blazars. And likewise, the Novi is led by basically an ex-student who's now on faculty in the US, Elias Adi. Other people, like even within the SALT partnership, but external to it, like people from the Rosetta collaboration, or some of our Polish colleagues have been leading things like nuclear transients in galaxies. So all of these different classes are things that we've observed, and different people take ownership and build up a sort of informal collaboration of a group of people where the people who do the work get the recognition in terms of the published papers. So it's not like many collaborations where it's like everyone is on the paper. It's only the ones who do any work that are on the paper. And of course, over the years, as I said, so I went forward to the last 2 points there. We've started to expand into multi-messenger follow-up, particularly, of course, with LIGO Virgo, and recently with Meerkat radio transients. So I'm just going to give you a flavor for some of the types of things that we've been doing. And the first one I want to talk about are the Novi. And until some years after the program began, no one was really paying too much attention to Novi at all until a young graduate student came up to me and said he'd like to observe some Novi. And I said, fine, go with it. He ended up being diverted from his major topic of his PhD, which was going to be MHD modeling, into Novi. His supervisor wasn't too concerned because she was also interested in Novi. And it ended up very well. He got a Hubble Fellowship at Michigan State, and now he's a tenured professor in at Texas. And he's done really seminal work on Novi, and many of it from observations that involve SALT and other facilities. And this first example is one of the first ones that he worked on, which was a very fast and very luminous nova in the Large Magellanic Cloud, of which the light curve is seen at the top right. And then the sort of low-resolution spectroscopy in the bottom left, all those lines there you can see in the early phase of the Novi. But then later on, the HRS spectrograph could do high-resolution imaging of the Balmer lines, where you see discrete clumps of material in the nova ejecta. So this really sort of showed that the SALT Transient program was excellent for Novi. And it went on to this interesting object, which was another paper that Elias led, which was, as you might have heard, Novi in recent years, maybe in the last 10 years, have been realized to be an important source of gamma ray emission. And this was a fortuitous event that there were some nanosatellites called BRICS, which I think was a Polish and maybe Canadian collaboration, 6 nanosats that were looking at really bright stars for pulsational sort of reasons. But just fortuitously, this nova that got to this 10th magnitude ended up being in the field of view for like 2 months. And so the top light curve there in red on the left is the light curve showing various flaring episodes in that period. And as it happened, Fermi Lat observed it half of it sort of simultaneous, and you can see the correlated gamma ray and optical flares. And this has sort of led to a revision of how we understand novae, and in particular the importance of shocks that produce high energy gamma ray emission. And of course, with this also, we got a lot of time-resolved high-resolution spectroscopy, of which there's examples of line profiles shown there. This has led to other types of outbursting systems. So this is work that's been led by Joe Philip Neenan and his student at TIFR. And this is beautiful data of an EXOR system. These are all salt spectra, high-resolution salt spectra that are taken during this last flaring episode. And the nice thing about it was that we had a meeting in South Africa on magnetism and accretion. And I persuaded Joe and his student to come. I think I might have even helped finance them. Anyway, they came to the meeting and they met, as happens at these multi sort of disciplinary meetings. They met Marina, I've forgotten her name now. She works at Cornell. She's an MHD modeler. What came out of this was that she applied her MHD models to the data that we obtained on SALT, and they published a paper on this system. And that just shows you, you know, the synergies that can happen sometimes just serendipitously. So one of the big sort of topics that we've been involved in is the follow-up of X-ray binary transients, both the high mass systems, of which there's a sort of cartoon of what that looks like on the left here. These are generally long orbital, usually eccentric orbits of a neutron star around a BE star. That's sort of a major class of high mass X-ray binaries. I mean, there are other ones. Cygnus X1 obviously is a black hole, which is also a high mass X-ray binary, but they're fairly rare compared to the neutron star systems. And the interesting thing about the BEs is that because of their rapid rotation, they're losing equatorial material. And because of the eccentricity of the orbit, the neutron star sometimes passes through that material and has what's called a type 1 outburst. And this is seen in X-rays, and follow-ups in optical can see how the lines change because of the interaction of the neutron star with that envelope or equatorial disk from the BE star. So we've done quite a lot of work on these, and in particular following up some of the new discoveries from Rosita in the Large Magellanic Clouds. The problem in the galaxy is that, of course, obscuration plays a bit of a role there. So the Magellanic Clouds has been a good hunting ground for these types of objects. Then the low mass X-ray binaries, of which there's a picture sort of showing the system in outburst with a bright accretion disk and a jet launched from the system, which you can detect in radio, and you can see how these evolve during an outburst from like a hard state to a soft state. The jet gets launched in that sort of transition. And so we've been trying to observe some of these during the state changes, and sometimes just observing them at high time resolution, which tells you quite a lot of other information that you wouldn't normally get. So in the case of the BEs, this is some examples of one such system that my colleague Itemelang Monageng has been involved in, of a SMC system. But generally speaking, we have typically long-term optical light curves for these systems, from OGLE particularly, but sometimes also from ATLAS and other optical surveys. And then, of course, with SWIFT, some of these can be followed up, or other X-ray satellites. And then we correlate that with the behavior of the emission line changes, which are seen here with high-resolution spectrograph observations of the H alpha line. So that's been quite successful. There's now numerous discoveries that have been made. Some of them show quite complicated behavior, not just a Gaussian type emission line, a multi-component emission lines, which we believe can be modeled. In fact, they've done SPH modeling now to explain the behavior of these more complicated emission lines. And some even discoveries of things like B white dwarf systems, which have been somewhat rare, but now there is a significant number, like 3 or 4 of them found in the Magellanic Clouds. For the low mass systems, as I say, some of these we've just been monitoring during a whole outburst cycle, a transitional cycle, which is over months typically. But we also do intensive observations. This is an example of a black hole system, SWIFT 1357. And this was known to be been seen in by previous people in outbursts as regular outbursts, and SALT observed 2 of these. And the interesting thing is that in the photometry, of which you see 4 light curves there, spaced, several weeks apart, you see these sort of non-periodic dips in the light. So they're not strictly periodic, but they're on a characteristic time scale, and that characteristic time scale evolves with time. In other words, the dips are more frequent at the beginning, less frequent later on. And this was seen by previous studies, and in fact, if you plot the characteristic time against the outburst time since outburst, you get that bottom left plot where you see the declining time between outbursts. The explanation for this is in this little cartoon here. Basically, the explanation that was put forward in this paper led by John Pace, which involved myself and Phil Charles and Poshak Gandhi and others, is that this is a much more luminous X-ray source than people had initially thought. The reason being is that it's heavily obscured by an inner torus or disk, and so the X-rays are not obvious because of that. And so the explanation for these dips is that there are some sort of extended, vertically extended structures in the inner part of this rotating torus or disk, which periodically block the central engine, which is responsible for the optical reprocessed X-rays. And so in this case, this whole disk and so on overwhelms the secondary star that you don't even see. It's a tiny little thing. And so that was the model that was put forward from just the photometry, but we followed that up with spectroscopic observations. And so now what we're doing is spectroscopy over a whole SALT track, which is shown here on the y-axis as, from 0 to 3,000 seconds. That's like the length of a SALT track. And these individual spectra were taken with something like, I think this was 30-second observations. So what was fascinating to see was the emission lines go into absorption. I mean, the emission lines are quite faint. You do see them when you co-add. You don't see them in this picture so much, but you definitely see the absorption components coming and going, just as you do in the continuum. But the fascinating thing is that you also see them in a high excitation line of helium-2, which is generally only something that you see in, supergiant, OB supergiants. It's never been seen before in a high mass X-ray line. So we did quite a few other observations of this at even higher time resolution, 10 seconds. And so what you then start to see, and I think maybe, hopefully you can see by eye, that those little dips that you're seeing up here, they're slightly diagonal. So they're shifting in velocity. And so that is like an interesting observation that might lead to some explanation through, like, say, an aspect effect or possibly deceleration of these absorbing blocks. But at the moment, the modelling is still to be done to try and adequately explain that. So I talked about E Rosetta. I mean, I think you've probably all seen this amazing image of the E Rosetta sky. And of course, it's completed 4.5 of the 8 scans that it was going to do before Russia invaded the Ukraine, and the Max Planck Institute put E Rosetta into a safe mode. And regrettably, no observations since, although data is still coming out of these surveys because they're still being analysed. Nonetheless, the results from that have been really interesting. I mean, one of the amazing results is the discovery of a different type of activity in the nucleus of a galaxy, so-called quasi-periodic eruptions in the soft X-rays of galaxies. And there was one previously known before the E Rosetta observations, and now there are, I think, 4. The first 2 shown here. And SALT was instrumental in getting the spectra of the galaxies to show that these were essentially red and dead galaxies. They weren't AGN, definitely. And they show these QPEs, I should say, with, you know, periods of a few to tens of hours. Apart from just those new discoveries, the sort of well-known, well understood AGN have also been observed, and in particular, using E Rosetta, there have been able to be detections of AGN going through on and off states, and so we followed up spectroscopically. This is an example of one particular AGN where on the left, you can see the X-ray emission was quite weak compared to like 6 months later when it was observed in the second survey. So, of course, people want to know what's the difference between it in the low state and the high state. So SALT has been useful to get spectra which show that, in fact, as you might expect, the sort of nature of the emission spectrum changes. And in fact, they change even from like a safe at 1 to a safe at 2 or vice versa. So this shows some examples of 2 SALT spectra at the top and middle, where you can see the broad component in the later observation is completely gone, and an earlier archival observation from 60F. So there's been a number of observations of these changing look AGN done within the SALT transient program. And then other types of nuclear transients like TDEs have been led by others. And so again, SALT has played a role in the regular monitoring of the spectra of TDEs as they evolve over, you know, timescales of months typically. And then the other thing that I'm going to finish with in terms of AGN are the flaring blazars, which is a program led by people at the University of the Free State in South Africa, University of Johannesburg, and Northwest University. And basically, they're part of the Fermi-LAC collaboration. So they're looking at the changing gamma ray states of many AGN, or many blazars, I should say. And they're obtaining SALT spectropolarimetry both during the flaring state and during the quiescent state. And so the plot on the left is just a normal SED showing the multi-wavelength behavior of this blazar. But on the right, there are observations that show the polarization detection with SALT in the spectropolarimetric mode. And what Marcus and his colleagues are trying to do is correlate the change in position angle of the linear polarization with the state change. And that can be used to infer about how the geometry of the jet changes in AGN. And one of the students at UJ has done a nice continuous survey of something like 30 blazars, which has just been published, showing these polarization changes. My own interest is focused on white dwarf binaries, although of course X-ray binaries is also my interest. So these are also transient systems. They're basically, you can think of a white dwarf binary, nothing with a white dwarf and a companion star, but not necessarily accreting. Cataclysmic variables are one subclass where there is Roche-Lobe overflow and there's accretion happening on the white dwarf. But increasingly we're finding detached white dwarf main sequence or even white dwarf other types of stars. And so we're looking at a wider class of such objects. And in particular, I'm interested in magnetically active or magnetic cataclysmic variables where the magnetic field of the white dwarf is sufficiently strong that it dominates the accretion onto the white dwarf instead of the formation of a disk. Sometimes the plasma from the L1 point just connects directly to the field line and is then funneled onto the white dwarf magnetic field. And that's why they're X-ray sources, because you get a huge concentration of very hot material and a shock produced within a confined magnetic tube on the above the surface of the white dwarf. So they then cool predominantly by thermal brainstorming and cyclotron emission. So that's why they're seen in X-rays, because of the strong hard X-ray component. And in optical, because of the polarized cyclotron emission, you see in their optical spectra, you can see cyclotron humps from the cyclotron emission, and you can detect the polarization as well, which can be up to many percent or tens of percent. One sort of subclass of these are super soft sources. So these are not magnetic systems. They're high accretion rate white dwarfs and cataclysmic variables, essentially, with an accretion disk, but they're accreting at such a high rate that they sustain constant thermonuclear burning on their surface. And so that's why they're very soft X-ray sources. This one here that I'm highlighting is the first example that also came out of Rosetta of a system which is the first helium accreting super soft source. And the salt spectrum, which is shown bottom left there, shows the spectrum is entirely dominated by helium light, something that has been looked for like 3 decades, the presence of helium-dominated objects, and finally realized. And this was a Nature paper by Joachim Greiner back in 2023. Also made a lot of use of test light curves and oval light curves where the optical orbital period was determined, which was then subsequently seen in the rate of velocity variations with the SALT HRS. That's recently been accepted, that result on the rate of velocities for publication. Magnetic CVs, I've already mentioned what these are. These are systems in which the white dwarf directs the accretion onto the poles of the magnetic field, shown in this sort of cartoon here. It's all happening down here, though, right at the surface, where you have a shock produced, and then the material cools by thermal brainstorming and cyclotron emission. But it's all coming from a narrow region, and because of the fact that these systems are short orbital period, and if you're lucky with the orbital inclination, they can be either eclipsed or they can self-occult as the hotspot rotates with the spin of the white dwarf. And so if you get high time resolution of the occultation or self-occultation or eclipse of the hotspot, you can probe it and determine not only its position, but you can determine a lot of other physical parameters like the temperature and the plasma density and so on. So these are systems that have been known for many years. I mean, ROSAT was instrumental in discovering many of these. but now there are significant new numbers that are being found in the eROSITA survey. And this is just one example that was followed up at SAO, both with SALT and the smaller telescopes. So in the left plots, you have a light curve that shows quite a lot of variation up and down. This is the eclipse here, this deep sort of square-bottomed one. This is a pre-eclipse dip when the accretion stream comes between you and the source of X-rays. But interestingly, you also see here the circular polarization, and that changes because of the orientation of the magnetic field. It'll be circular when you look down it, it'll be positive or negative whether you're looking down or looking up. So a number of these have been discovered through eROSITA, and some SALT time has been used to follow up on those. And this is an example of another magnetic CV that was discovered by the Einstein probe. This is a different class of magnetic CV that the fields are not strong enough to synchronize the white dwarf rotation with the orbital period. So in fact, when you look at the power spectrum, you see, not only do you see the orbital period signature, which is 3.7 hours, but you also see a 238-second spin signature. And we followed this up with some of the smaller telescopes, but then we looked and did spectroscopy with SALT, and this is where the wonderful capability of time-resolved spectroscopy comes to fore. These are 30-second individual observations, so 30-second spectra stacked up over a whole SALT track. So the 3,000 seconds in the SALT track, so there's 100 spectra all stacked up there, and on different nights as well. And what you can see is that you see sometimes a sort of narrow component, but then you see this broad component going out into the red wing here. And that's been interpreted as evidence that it could be a propeller system, that there's material that's being flung out from the system. Not only is it accreting, but it's also propelling material. So this is sort of perhaps a white dwarf analog of what might be a transitional millisecond pulsar, of which we've only ever seen one that's gone between an accretion state and a propeller state. Normally it's one or the other. So other things that we've done is follow up active stars, so from the discovered from Meerkat. So for example, in the early days of Meerkat, there were a number of radio transients, and this is an example of one that was observed with SALT. So these are systems that are binary stars, typically in a 10-day or 30-day period. This one was sort of interesting in that it was sort of at the high end of orbital periods, unusually active for such a long period system. And I've had a student working on the Meerkat galactic plane survey, and he's been finding many more examples of both flare stars and these binaries, which we've been also following up with SALT. Just to finish off with these sort of list of different things we've observed, SALT is really hard to do gamma ray burst follow-up because typically you need to be on the source within the time of the alert, so as soon as you get the GCN alert and it's bright enough, you have to go for it. And typically with SALT, because it's restricted window, you typically take hours before it's visible, which is why we've only observed something like 4 GRBs in the whole time SALT's been operating. But nonetheless, we have been lucky. This is an example of one such lucky coincidence, or not coincidence, just lucky that we observed this particular one in 2019, which at its brightest got to 10th magnitude. That's really bright for a GRB. But even when SALT got onto it 3 hours later, it was down at like 17th magnitude, so still observable. And then like 10 hours later, the VLT also observed it. So what we got out of this was spectropolarimetry, because you need it to be bright if you want to do spectropolarimetry. So both SALT and VLT confirmed that it was sort of polarized at about 1.5% model level. It wasn't sort of fascinating from the view of like it was just really consistent with a forward shock, maybe a fresh shock because there was a plateau phase, which you can see in the light curve here, even maybe a slight rebrightening during this period here. So the SALT data were taken here in this part and the VLT here. So that led to a paper in 2021 on the spectropolarimetric observations of that source. And then to just go on to even the more energetic things, and you can't really not talk about this, GW 170817. So we were very, very lucky because there were only 2 days, 2 nights that we could observe this before it was lost into the twilight sky. And we were lucky enough to observe it on those 2 nights. So the first observation, which is the observation up here, this one, is 1.2 days after the initial gravitational wave and gamma ray signal. So, of course, we were lucky with that. We observed it on the second night where the flux was much fainter and it was much redder. And then it was followed up by a number of other facilities with smaller telescopes as well. Of course, with the subsequent campaigns of Virgo LIGO, like 03 and 04, there haven't been any more discoveries, and 04 has sort of gone backwards because the localization was even worse than it was in 03. So we were hoping 04 would lead to some, but nothing as of now. So I'm going to finish now with the sort of last part where I was going to talk about other future of transients. And of course, the next big thing in discovery space will be Rubin, which is an amazing facility. You can see a picture of it here. And as I said, it's going to be hopefully starting to send out alerts imminently, like it was due to happen tomorrow. But with this hiccup with the camera, not yet. So the idea is it's covering a large amount of the southern sky, even into the north, up here, the north ecliptic spur. But the most dense observations will be in this green region here, where we're expecting something like over the 10 years of the survey to get something like 800 to 900 observations over that period of time within that period. And in terms of transient or variable, I mean, the word transient gets loosely used because they also talk about anything just varies, so it might be a known variable style, whatever. 10 to the 7 alerts a night are expected. Of course, that's down to the limit that LSST will go, which is like 27th magnitude in co-added images. So most of those you just ignore because even with SALT, we can't follow up things that are much fainter than 21. So that's why machine learning, artificial intelligence is so important. Well, a lot of people have been working on brokers to try and sift through to select things that are more compelling. Much as I'm interested in CVs, I don't want to look at all the dwarf novae in the galaxy, which will be an overwhelming number every night will be discovered, or flare stars. But things that are more interesting will be. So, of course, the problem with LSST is how do you do the follow-up? And so in South Africa, we've had this program going now for nearly 5 years called the Intelligent Observatory. And the idea is to use some of the telescopes that we have that we can utilize and network it into a totally automated follow-up machine that takes alerts and makes decision-making on what to observe. So at the moment, we have 3 telescopes that have been incorporated into this intelligent observatory. And one of our hopes is that we will add other telescopes that may be hosted by some other facilities, like, for example, the Monet 1.2 meter telescope, or the Prime 1.8 meter infrared telescope. But this is paving the way for a sort of global approach to doing transient follow-up. And this is something that I've been pushing through the BRICS astronomy program for some years. And in fact, there was a program that was adopted in 2019. So in 2017, here at IUCAA, we had a BRICS astronomy meeting. And at that meeting, it was decided that there would be a flagship program within BRICS astronomy. And so a call went out for concept proposals for what such a flagship could be. And the bottom line is 2 years later, this program called the BRICS Intelligent Telescope and Data Network was approved at the meeting in Rio in 2019. And the idea is that this is a two-phased approach, taking advantage of existing telescopes and future ones. So the ones in South Africa, some of them I've already mentioned. These are some of the ones that will be involved in the Intelligent Observatory. But within the BRICS flagship project, which is a big project, it has something like, what did I see, over 108 co-investigators. Many people from India put their names on this list back in 2018 when the proposal was put together. And so the idea is to start modestly, to use existing facilities that we have access to within the BRICS family. So, you know, each of the different countries have either their own telescopes or access to telescopes. I'm showing Germany here, which is not owned by a BRICS country, but Brazil has time on it, as it does on the SAW telescope. SALT, obviously, the 6 meter in Russia, the Lamos telescope in China, and of course the DOT in India are all facilities that could be used in transient follow-up. But a lot of this will require like photometric observations, imaging observations, and maybe the easiest way to start this is to extend what we're doing in South Africa with the 1 meter class telescopes or 2 meter class telescopes in utilizing what's already at other observatories in the respective countries. And I've shown some of the ones here that might be utilized in this initial phase. But we were told to think big back in 2018 when we came up with this flagship project. So the second phase is this ambition to go to a globally distributed network of telescopes that would cover the entire sky and to push to a cadence which has never been achieved before. So this is a diagram showing the magnitude limit, and this is the cadence. In other words, how often you observe that field. So up here is LSST. It's going in individual exposures to 25th magnitude, really, really faint. But it's got a fairly poor cadence of a few days. And there are other facilities that are already better in terms of cadence, like Atlas and so on. But ideally, we want something that's going to move, maybe not fainter because we'll just be inundated. I think a 20 or 21st magnitude cut would be fine, but to move to a higher cadence, and that's the sort of motivation for the second phase of this BRICS project. And so it started off now with a program that was already happening in China called CITIUM, which was basically to build a lot of these telescopes and site them in China. And they've already produced 2 telescopes as prototypes, and they're basically a modified sheath design that allows you to get in a single exposure 25 square degree field of view. And it's using these state-of-the-art large format CMOS cameras. So this is a 2x2 array of 8K 10 micron CMOS cameras from G-Pixel in China. And at the NAOC labs, they're manufacturing these cameras to exploit these big chips. The current one is at the Jinglong station where Lamoste is, which has to be said is not the best site. It's a convenient site, so it's good to sort of do a prototype test. But the second telescope, which is planned to be installed, has been completed, will be at their new site in Tibet, in the northern part of Tibet at Lengqiu, which is also the site of their just approved 14.5-meter segmented mirror telescope. But the idea is to extend this outside of China and make it an international project, and to have ideally 135 of these 1-meter telescopes grouped in groups of 3 with a dedicated filter per telescope, because there's no room up at the prime focus for filter wheels. So 3 telescopes would be observing the same field with different filters at one time. And that's a concept of what's called a global open transient telescope array, or GOTA. So the plans for moving forward, last year I was at an AI in astronomy meeting. Ajit was at that meeting as well. And at that time, we signed an MOU for both the 2 1-meter telescopes in China, but 2 0.5-meter telescopes, AI-enabled telescopes, to be built and paid for by China, but hosted in Brazil and South Africa. And I'm hoping that MOU that will confirm all of this will be completed very soon. So, we're ready to plan for the installation of further telescopes within the BRICS countries. Now BRICS is more than just the 5 original. There's 5 other countries now. And some of those countries, I think, would be interested in hosting some of these telescopes. And I'm hoping that India will join this endeavour. Certainly, the original concept, the proposal was supported. The science we talked about was supported back in 2019 when we first, had this approved. But regrettably, there's been little sort of, interaction between the Indian community and the BRICS astronomy group. So there haven't been, for the last 2 meetings at least, either no attendance by Indian representatives, little attendance. So I hope, maybe from what I've said here, that I might re-enthuse some of you who might wonder what happened to this project, and try and really get something, because I think within our family of countries now, we can do things that are internationally competitive, not being really thought about by other countries. And in certain other countries, science is no longer being supported, right? So internationalizing things is more challenging, and just from a budget point of view, unlikely to happen. So with that, I think that brings me to my last slide, and thanks. Yeah, happy to take questions.
Thank you, David, for sharing exciting transient science and the future as well. Questions? Yes.
So I wanted to know what is the fraction of these different targets that you have. And typically,
You mean the ones that we observed?
That you have observed in the program so far?
Of the different classes?
Yeah.
That's a dynamic thing. So I can't say, like, this semester, 25% of them were low mass X-ray binaries, because it's a number that goes up and down.
Fluctuating.
It fluctuates, yeah.
But depending upon the interest, or depending upon the targets that, so that would be the question. And then the other part is how quickly can you go on to a target? Typically, Is this within like a day time scale?
Yes.
What is the
Yes.
um,
Yeah, I mean, my typical modus operandi is that I look at my email before dinner and I see if anyone's sent me something. And then if I have time, I put something in the queue. Because at the moment we're sort of small, we can handle things in a manual thing. We have developed an API to be able to do this automatically, but we have to be very careful about how we filter, because we don't want to put in things that are maybe not appropriate or difficult to do. So there's still a manual at the moment, manual process. And it's not like we can use all of this all the time. I mean, we get a good fraction of it, but we have to be selective. But it's a very open collaboration and by nature dynamic, sort of responding to how discoveries are being made. And so although it's like a SALT program and we have SALT partners, including IUCAA, we also have people outside of SALT involved in it, like the German group at MPE and Potsdam. And that comes and goes as the demand comes and goes.
thank you.
Hi, David. Thank you for a very nice talk. It's truly inspiring and informative. So I just had one science-related problem I wanted to ask you. That if we are observing, for example, using HIS spectrograph, and if we observe some extended objects such as the planetary nebula,
If you do observe what?
extended objects like planetary nebula and all. So in that case, if we use 1x1 beaming detector, will it be enough to completely get the data from the whole of the nebula or not? So
Not with the high resolution spectra, because you're dealing with two fibers and they're really for point sources. So these fibers are typically 2 arc seconds or 3 arc seconds in size. We have a number of them where we slice the images so that we can get higher resolution. But it's basically designed to do the point source and some background, although for many cases the background's insignificant. So to do an extended object with HRS is really not on. But what we do have now, and I should have mentioned it, I didn't update the slide, is that we now have, courtesy of Sabyasachi, who was at the observatory for a number of years, a fiber IFU, slit IFU. It's a very clever technique where in the focal plane, where you would normally put, say, a slit mask or a long slit to do normal spectroscopy, instead you put in this sort of flat structure that has little prisms and then diverts the light into a fiber IFU, and you can sample, over a field of view. And I have successfully used that. In fact, I think one of the first papers that will come out with scientific results from this fiber slit mask will feature an observation we did of a BE X-ray binary in the Small Magellanic Cloud, which has a nebula around it. And we wanted to see what are the ratio of the emission lines in the nebula, like the sulfur, nitrogen, and H-alpha, to say, is it possibly a supernova remnant, or is it just an H2 region? And we're able to address that with that very nice recent addition.
okay, so what do you suggest would be the best binning for this kind of sources if we are planning to observe in optical? So what is the most optimal configuration for observing this kind of objects?
For observing planetary nebula or extended objects?
Yes.
Yeah. Maybe 8 years ago, I would have said the Fabry-Perot system on SALT, which regrettably has not been a success and really, I think, has been essentially dropped now, despite the fact that we spent a hell of a lot of money on Etalons. There were just so many sort of challenges with that system up at the prime focus. So that doesn't help you, because that would have been something that you could use. I used it on supernova remnants in the the Magellanic Clouds. But there really isn't something other than this fiber IFU that I've just talked about, which you could use. Now, that could be fine for your purposes because, I used it on this this compact B X-ray binary with a nebula around it. It was really designed to do galaxy spectroscopy, but it's using the existing suite of gratings with the RSS spectrograph. So you still have the flexibility to, to choose whatever grating you want and therefore be able to. I mean, I should say that it's only within, I think, a 25 arc-second field of view. So even though it is extended, it's not like wide field. It's not taking up the whole 8 arc minutes of SALT. But maybe for some systems that would be okay. And I think there's a second one that Sabyasachi's built, which is maybe bigger fibers and bigger field of view, but I'm not quite sure. And then in the infrared, the Neurals instrument is also an IFU, but again, not huge. I've forgotten what the size is, but yeah, so there is some, but you have to bear in mind also that it's quite a lossy system. So compared to what you would get just with normal long slit, you'll get much less, but you'll get the spatial coverage. And if it's got a high surface brightness, then maybe it's okay.
Thank you so much.
Okay.
Maybe I can ask you. So my favorite sources are these quasi-periodic eruptions.
Sorry?
Quasi-periodic eruptions.
Yeah, those QPUs. Yeah.
Yes, we are actually observed we was there with AstroSet, and we did not detect any changes in the UV emission during the soft X eruptions. So I was wondering, soft being of course much more sensitive, whether people notice any change in the optical emission during the eruptions particularly.
We haven't looked, to be honest, because when I spoke to what was in Riccardo Arcodia, who was like the guy leading that follow-up from Rosita when he was at MPE. I asked him, what do you think are the prospects of doing other wavelength follow-up? And he said, it's only been seen in soft X-rays. So I was sort of put off. But on the other hand, if you don't look, you don't find it. So I've always wondered, I'm one of those people that likes going on fishing expeditions. And, sometimes you catch something, sometimes you don't. But when you do, like recently, I went on a real fishing expedition with my son-in-law in Cape Town on a boat, and we caught 8 over 40 kilogram yellowfin tuna. That was very successful fishing expedition. So maybe that's worth looking at, and I'll think about that now that you've prompted me, because what can you lose? Yeah.
Any last questions? So let's thank David for